Today we're going to look at using rational exponents. So what's a rational exponent? Well, what's a rational number? Remember that a rational number is a number that can be written as a fraction. So a rational exponent is an exponent that can be written as a fraction, like x to the 1/2. So what's x to the 1/2 mean? Well, let's take a little bit closer look at x to the 1/2. What would happen if I squared x to the 1/2? If I squared x to the 1/2, thinking about properties of exponents, that means that I multiply those two exponents, 1/2 and 2. But 1/2 times 2 is x to the 2/2, and 2/2 is 1, or just x. That means that x to the 1/2 squared is the same as x. What other expression do we know that when we square it, we get x? A good candidate, the square root of x, because we know that the square root of x squared equals x. So if x to the 1/2 squared equals x, and the square root of x squared equals x, then it must be true that x to the 1/2 squared is the same as the square root of x squared, or x to the 1/2 is the square root of x. So what does x to the 1/2 mean? It means that x to the 1/2 is the square root of x. Let's look at some examples. 7 to the 1/2 means the square root of 7. What happens if I make it 5 to the 1/3? Now it's not the square root of 5, but the cube root of 5, because if I cube 5 to the 1/3, I get 5 to the 1. If I cube the cube root of 5, I get 5. How about 5 to the 2/3? Well, here we're going to break that apart to 5 to the 2 times 1/3, which means 5 squared to the 1/3. Remember, I can multiply exponents, and that means the cube root of 5 squared. Or if you want, you can think of it as the cube root of 25, but we're going to leave it as the cube root of 5 squared. Here's another example. How about x to the 3/4? Pause the video, write down what x to the 3/4 should equal, and then play the video again and check. You should have gotten the 4th root of x cubed, because I could write that as x to the 3rd to the 1/4 power. So my index is the 4th root. How about evaluating expressions that contain rational exponents? Let's look at something like 27 to the 2/3. Now you could change this to a radical, but that really is kind of ugly. Much easier if we leave this as an exponent and we take advantage of the properties of exponents that we know. So 27 can be written as 3 cubed. If I take 3 cubed to the 2/3, that means I multiply those exponents. 3 times 2/3 is the same as 2. So I have 3 squared, and 3 squared, you know, is 9. Look at another example, 32 to the 3/5. Now I want to think about what number I could change 32 into so that when I multiply those exponents, I end up without a denominator. So I can think of 32 as 2 to the 5th. Convenient, because you'll notice that when I multiply 5 times 3/5, those exponents, I just get 2 to the 3rd, and 2 to the 3rd is 8. Notice, no radicals needed. Very important idea. Keep away from the radicals and use the power of exponents to simplify. How about operating with rational exponents? Let's multiply expressions with rational exponents. You know when you multiply with exponents that you add the exponents. We're going to do the same thing here. X to the 2/3 times x to the 4/3, because I have the same base, I can add the exponents. And 2/3 plus 4/3 is x to the 6/3, which reduces, of course, to x squared. What about if I divide expressions with rational exponents? Well, when we divide, we subtract the exponents. So if I have x to the 5/3 divided by x to the 2/3, I want to subtract the exponents. 5/3 subtract 2/3 is x to the 3/3, or x. What about if I find powers? Remember, when we take powers, and we've actually been doing that, when we first defined what an expression containing rational exponents is, we multiply the exponents. So if I have x to the 2/5 to the 4th power, that means I multiply those two exponents, 4 times 2/5, to get x to the 8/5. What would I do if I had x to the 3/4 plus x to the 1/2? Can I add these? Well, remember, adding relies on the distributive property. So if I think of this as 1 times x to the 3/4 plus 1 times x to the 1/2, I would have to be able to factor something out so that I'd be unable to just get 1 plus 1. But what would I be able to factor out? X to what? Well, it doesn't work. And because it doesn't work, we know that we must have the same base and the same exponent if we want to add. So multiplication, division are good, finding powers is good, but just like when we operated with radicals, you can't add unless you have the same base and the same exponent. There's one last thing I want to look at. I want to go back to that x to the 2/5 to the 4th power. We said we needed to multiply our exponents, so we had 4 times 2/5, which was 8/5. Let's take another look at x to the 8/5. X to the 8/5 is x to the 5/5 plus 3/5, or x to the 1 plus 3/5. And remember, that was really the result of multiplying exponents. So that's x to the 1 times x to the 3/5, because when I multiply exponents, I add them, which is x times x to the 3/5. Now let's go back. Look at x to the 8/5 again. X to the 8/5 means the 5th root of x to the 8th. Breaking out powers of 5, I could write that as x to the 5th times x cubed. So the 5th root of x to the 5th is x, and the 5th root of x to the 3rd is the 5th root of x to the 3rd. So you'll notice those two expressions are really the same. X times x to the 3/5 is the same as x times the 5th root of x cubed. So I can take advantage again of the power of exponents to be able to simplify radicals if I want. And I don't need radicals to do that. This, by the way, shows one of the nice connections between radicals, rational exponents, and the rules for operating with radicals and rational exponents. So now you have two ways to operate with radicals. One is by using radicals, and one is by using rational exponents. Your choice, and sometimes one way is easier than another. Okay, that's all we have for today. Please make sure that you do some practice problems. If you've got questions, talk to a math teacher near you.